the lab that we were working on last Friday and then spent some time yesterday, how much more time do people need on that? Or are you, at this point, relatively good to go? Or, let me ask questions with opposite answers. Who needs more time with your group on that? Okay. How much more time?
15 minutes.
10, 15, good for, all right, so let me set my alarm for 15, that give you a chance to actually get stuff. See, we've done that, so we'll do about a half-hour class and then break off, and then you can work on it or whatever you need to do. So 11:35 a.m. All right. We are here. Any questions on chapters 4 and 5? 4 or 5? Any questions on chapters 2 through 5? All right, just wanted to give you the opportunity. So this will be the first material that is not part of the first test. And they started out with the same question. On the worst case scenario, it becomes a read my mind exercise, and I got to a point where I thought, all right, so how do I ask the question in order to get the answers I want? And so I posed this to my wife and daughter, and what they came back with was exactly the same question I was asking. So I don't have a better way of asking it. I have object A here, careening to the right. I have object B here, careening to the left. They will collide. They will collide at this line right here. So this is the point when they first touch each other. A and B. They will, in this particular case, they will bounce against each other. This is the point when they separate. So they're going to hit, there'll be some movement, and then they will separate. And then in this particular scenario, A will go back this way, and B will go back that way. The box B should be the same size in every drawing, and the box A should be the same in every drawing. For those who don't completely follow the panel drawings that I have here, here's the next visual. That's what's going on. So they collide, there's some movement while they're touching, and then they separate. Any questions on this? What's the scenario? I haven't asked the question yet, but any questions on the scenario? Or scenario, less muffled.
They're the same size, you said?
Not necessarily.
Oh.
As in, this box, that box, that box, and that box are all supposed to be drawn the same size.
Oh, all of these and eight, okay.
Yeah. I'm not trying to indicate that B got squished. It's just that I can't draw. All right, so the question is, while A and B are touching, comma, they each have three quantities which are the same. What are the three quantities? And a quantity, just something that can be measured. Not necessarily that we could measure it, but it is possible to measure it. And just to add a little bit of excitement to it, can you come up with the three before the man gets hanged? All right. What is a quantity that would be the same while they are touching?
Mass.
Not necessarily.
Normal force?
Expand on that.
Well, since they're each pressing against each other, and I guess I would be assuming that cancels each other out, like it's 0 before it's shifted. So each direction it will cancel out and it'll be 0. So each side would have the same normal force because they're touching.
I'll agree with part of what you said. I'm not gonna quite put another body part down, but someone want to clarify or cut off the part that was incorrect?
Cancels out is incorrect? The cancels out is incorrect?
That is incorrect. Yeah, true. Yes. The force, when you talk about canceling out, you generally talk about forces acting on one object. So if you're talking about normal forces canceling each other out, what object are these normal forces acting on?
Against each other.
Yeah, that has to be forces have to act on a single object to cancel out. All right, so what does that leave us with the part that is true? Or almost true? What about the normal force?
That it's present.
Okay, I'll agree. In this particular example, there's a normal force. I will agree with that. What is the same concerning the normal force?
The magnitude?
Say the whole sentence.
The magnitude of normal force is the same?
Something for a little bit more.
For A and B.
All right. The normal force they exert, the magnitude of the normal force they exert on each other is the same. Yes, normal force is the same. So I'm going to write it in shorthand. Actually, I'm going to write it out, then I'm going to do the shorthand notation. So normal force A exerts on B as same magnitude as normal force B exerts on A. Now originally what I heard Rachel say was that the normal force was the same. Why do we know the normal forces are not the same?
Because it's opposite direction.
Exactly. Okay. So here's the shorthand notation. And this actually works for any interaction. It doesn't have, in this scenario it's a normal force, but it actually works for any other forces that happen to be involved between two objects. The force on A from B, so that is the force on A from B, equals, and the negative sign is indicating direction, it's the opposite direction, the force on B from A. This right here, this is just the shorthand notation for Newton's third law. All right. So we got one of the three, two more to go.
Friction.
I will say that the forces are covered at this point. Whatever force that A exerts on B is matched in magnitude by the force that B exerts on A, whether it's friction, normal, gravitational, whatever the force happens to be. There are a limited number of quantities we've studied, so. And one of the answers is so incredibly obvious once you hear it that most people don't think about it.
Throwing it at the displacement.
What do you mean by displacement?
They'll have started here and they're together, and then they've moved away again. Was that position?
Not what, again, part of what you said is right. Part of what you said would add another body part. At this point, we have two halves. I think that's gonna make a hole there. All right.
The acceleration of A is.
Are you offering acceleration, or are you just thinking out loud at the moment?
I was offering, but now I'm not offering anymore.
It sounded like you stopped mid-sentence, that's why I was wondering.
Yeah.
All right, I'll wait till you're officially gonna offer it. All right, now what Carrie said was a half, so obviously part of what she said can be explored more, or you could just ignore her and just go on with something else.
Would it be the displacement from when they touch and then they move over and then they separate, like that distance that they move while they're touching?
Yeah, because if you think the center of mass of A will travel that far, the center of mass of B is gonna travel that far. Their displacements are the same while they are touching, because remember, it's while they're touching. All right, so we have the displacement of A while touching is equal to the displacement of B while touching. And one more, the one that's so obvious, it's usually ignored. And given enough time, I'll give one of my more obscure clues. All right, the obscure clue. It's the name of a Bobby Sherman song. I did have a student years ago who actually knew who Bobby Sherman was, but he had been to a concert even. And at some point, since the start of class, I've actually said the answer. Not in, yeah, I've used the word, I should say. Think about the quantities we've studied, things we've assigned numbers to.
Velocity?
First off, they start out traveling in opposite directions, so when they first start touching, their velocities can't be the same because they're opposite. And then at the end, they're in opposite directions. So velocity is not the same throughout the touching. I think it's also the name of Pink Floyd's song. I have to double check that one. How many things have we seen?
Would it be distance?
That they travel the same distance while they're touching? Since the displacement is in one direction, yeah, you could get away with that. I wasn't thinking about distance. In this particular case, since in my scenario they touch, they move in one direction and then they separate, the magnitude of the displacement would be distance in this case. So yes, so not a body part, but not the one I want.
And you said it wasn't acceleration?
I actually did not comment on acceleration.
Could it be the acceleration while they're touching?
It actually won't be. Because for one thing, the forces are in opposite directions, so the accelerations have to be in opposite directions. If you're talking the scalar acceleration will depend upon the masses. So think about, you're traveling along and a bug hits your windshield. The car and the bug definitely experience different acceleration, even though they exert the same force on each other. Apparently this group is not up on their Bobby Sherman songs. It's about depth, does that, it flies? Tipus fucid.
A bird. A helicopter.
Something more physics related than, I guess those are physics related. Something more esoteric than a physical object that flies. That clue went unnoticed.
Set inertia. That was my guess.
I guess inertia technically is a concept, it's not a quantity.
Oh.
Like pointing at my wrist is, I'm not quite sure why that would be inertia though. Yes. The Bobby Sherman song, time. We all die sometime, no matter who you are or what you do. We all gotta go. We all gotta die sometime. It's an upbeat song. Time. They touch each other for the same amount of time. I told you, it's incredibly obvious once you know it. They touch each other for the same amount of time. So the time of A is equal to the Take time to beat. All right, so why do I make you go through this? Well, partial explanation is that if we combine these two ideas, the fact that they exert the same magnitude of force but opposite directions on each other and undergo the same displacement, this introduces us into chapter 6, energy and work. If we take the Newton's third law and and the idea that they exert the same force on each other for the same, or they touch each other for the same amount of time, this gets into into chapter 7, which is impulse and momentum. We're going to take what we've learned so far with Newton's laws and with our ideas of velocity and acceleration, and we're going to manipulate them so we can look at the exact same things we've been doing in a different way. And it's going to offer us some more tools in the tool belt for being able to be able to predict motion. Now, what I'm about to do, much to the delight of 110 students every semester, is I'm going to go through a derivation. What I'm about to do is I'm not going through the derivation because I want you to regurgitate it later. What I'm going to do is, without it, a formula is just going to appear out of nowhere. And I want you to see that there is some connection between what we've done and what we will be doing next, that there is some logic to it. So, if your math is weak, then some of this you just sort of let flow over you. But I'm going to start out with the idea that the force on A from B is equal to the negative force on B from A. I'm now going to multiply both sides by the displacement that they undergo. So the force on A from B times the displacement on A is equal to the negative force of B on on B from A times the displacement. All I did is multiply both sides by the same thing. They have different subscripts there, but they're equal to each other. Newton's second law. What is Newton's second law? That's first law. It's the math equation. The most important equation, is what I refer to as the most important equation in all of physics. Apparently it had a huge impact.
Oh, mass times acceleration.
Okay. Force equals.
Force.
All right, so what I'm going to do is I'm going to use Newton's second law here. Newton's second law. And so this force on A has to be equal to the mass of A times the acceleration of A. And this would be the negative mass of B times the acceleration of B dot something xB. Have we done dot products, talked about dot products at all? Okay. There's a dot in between here. This is supposed to be a dot. It's multiplication. There's two ways of multiplying with the vectors. One is called a dot product because you use a dot. The other is called a cross product because you use an X or a cross. This is a dot product. So this symbol right here is there for a reason.
Does it change anything? Because you're just multiplying.
Yeah, but how do you'll take direction into account when you're multiplying? That's what the dot, that's the difference between the dot and the cross, is deals with direction. So let's talk a little bit about, we'll do one other thing and then we'll talk about the dot product, or most likely that'll wait until Monday after the quiz. What is acceleration? The formula.
Change in velocity over change in time.
That's the one. So this is mass of A times the change in velocity of A over how much time took place. Dot delta, and displacement. Now what's the formula for average velocity? Or I guess in class I started out with just the formula for velocity.
Distance over time.
That would be speed. Almost there.
Position.
I
Change in
need more than
position
that.
over change in time.
Say it again?
Change in position over change in time.
Yes. So change in position over change in time, or displacement divided by time. So this delta x is equal to the average velocity times time. Just multiply both sides by time. Cancels out on the right, and on the left it shows up. And for some reason I decided to reverse the order in which I'm writing it. If acceleration is constant, how do you find average velocity? We did a number of examples in class. I did the table, we had time, we had velocity, we did the whole thing, and I said, how do you find the average velocity?
The first and the last.
Yeah.
divided by-
And so
Or
we're gonna,
divided by how many?
or in this case, we'll just take the first and last and divide by 2. Vi plus Vf divided by 2. So the initial velocity plus final velocity divided by 2. So what I'm gonna do here is I'm gonna make that substitution in here, so I've got initial velocity plus final velocity over 2 times time equals, and then we have to do the right-hand side. Do one other thing here on the left-hand side. MA, change is always final minus initial. So this is VF minus VI over however much time, dot VF plus VI over 2 times time. And on the right-hand side, negative MV, and then, this is all for A, and A, that will make a difference. And over here, we have VFD minus VIV over the time, dot VFD plus VIV, VIA, so V over 2 times time. So that's slightly more than that. All right. We've got a couple more steps. It's gonna look like a huge mess, and then it'll simplify all in the end. That's where we're heading. It will get nicer. Again, I'm not doing this because I'm gonna ask you to just spew it all back to me at some point. I just, again, want you to understand what we're coming up to comes from. And we're gonna have to leave a cliffhanger here. That alarm was to give you time to wrap up that lab. And even though, no doubt you'll be thinking about this until Monday, don't forget, you do have a quiz on Monday on chapters 4 and 5. So don't forget to study for that. And I guess you know where the equipment is, so